Hi, my name is Xiaodong Jia, a PhD student at Penn State. I will present an efficient and formally verified parser generator for visibly pushdown grammars. Visibly pushdown grammars, or VPGs, are a subset of context-free grammars, or CFGs. A CFG is represented by four elements: the set of non-terminals V, the set of terminals sigma, the set of rules P, and the start symbol L0. In a VPG, sigma is further divided into three disjoint kinds: the call symbols, the plan symbols, and the return symbols. We will mark a call symbol with a left angle bracket and mark a return symbol with a right angle bracket. The kind of a symbol determines the stack action. For a call symbol, the action is to push. For a plan symbol, the action is to do nothing. And for a return symbol, the action is to pop. A VPG also restricts the forms of the rules. We can only rewrite a non-terminal L to an empty string, or a terminal followed by a non-terminal, or a non-terminal surrounded by a call and a return symbol, followed by another non-terminal. For simplicity, this talk is only about well-matched VPGs. A well-matched VPG requires that the terminal in the second form must be a plan symbol. Our paper constructs parsers for general VPGs, where the terminal could also be a call or a return symbol. Here is a toy example for XML document specified by a VPG rule. Below shows a piece of XML document and how it is captured by the rule. The expressive power of VPGs are between regular grammars and context-free grammars. VPGs are more expressive than regular grammars because it allows nested structures with the help of call and return symbols. VPGs are less expressive than CFGs since the plan, call, and return symbols must be different. Below is an example grammar that is CFG but not VPG. Intuitively, the terminal C is both a call and a return symbol, which is not allowed by VPGs. Both VPGs and CFGs can be converted to pushdown automata, or PDA. VPGs determine the behavior of the PDA. For a call symbol, the PDA must push something to the stack. For a return symbol, the PDA must pop the top of the stack. And for a plan symbol, the PDA must not change the stack. Therefore, it is always possible to build a deterministic PDA for VPGs, which is not always true for CFGs. This allows us to parse VPGs in linear time, which is much faster than parsing CFGs. We believe that VPGs are promising for parsing, since it is very efficient to parse VPGs. And compared to other grammars, VPGs are less of a burden to developers. Also, as we will show later, VPGs are pretty expressive for practical usages. We have the following contributions. First, we provide efficient VPG-based linear time parsing. Our generated parsers accept ambiguous grammars and produce a parse forest containing all parse trees for the input string. When the grammar is unambiguous, the parse forest is actually a parse tree. Second, we provide a derivative-based algorithm for converting a VPG to a deterministic PDA. Third, we provide a formally verified parser generator in Coq. Finally, we provide a conservative and sound algorithm for converting tagged CFGs to VPGs. Our tools have the following workflow. First, the parser generator accepts a VPG and the corresponding semantic actions and produces a parser for the VPG. The parser then accepts an input string W and returns a parse forest embedded with the semantic actions. A parse tree can then be extracted from the forest, and its semantic value can be computed by executing the semantic actions in the parse tree. Our parser generator is formally verified, meaning that the parsed forest generated by the parser is sound and complete, which means the forest contains and only contains the valid parse trees for the input string. Now we will introduce the derivative-based recognition for VPGs, which is the basis for the parsing. In the recognition, we convert a VPG to a deterministic PDA, which recognizes the same languages of the VPG. In the PDA, a state S is a set of non-terminal pairs LC and L. L is the non-terminal to be parsed next, and LC is called the context non-terminal, which means LC was used to derive L without consuming an unmatched call symbol before getting to L. The initial PDA state only contains the pair of the start symbol. A PDA stack contains the pairs of a PDA state and a call symbol. The initial PDA stack is empty. A configuration is defined as a pair of a PDA state and a stack. The PDA makes transitions from a configuration to another configuration based on the input symbol. The transitions are computed by the derivative functions. So, what are derivatives? We can compute the derivative of a language with respect to a symbol C by taking all strings from the language that start with C and removing the first C from them, and only keeping the residual strings. We specialize the derivative functions to the configurations and introduce 3 derivative functions corresponding to plan, call, and return symbols respectively. Here is an example grammar and the recognizer PDA for it. For the input string ACDB, the choice of running the PDA is shown below. Since the last configuration is an acceptance configuration, the string is accepted by the recognizer. The correctness of the recognizer is formally verified in Coq. The idea of building PDA also goes for the parser. For the same example grammar, we build a parser PDA and run it on the input string. The following shows the transitions. The parser starts at the initial state, reads the symbol, and makes the transition based on the symbol. After reading all input symbols, the PDA leaves the trace of states. Each tuple in a state corresponds to a rule. For example, the tuple ACC in the third state corresponds to a rule that rewrites A to CC. The trace contains all sequences of rules that generate the input string. That's why we will call the trace a parse forest and call each tuple in a state an edge. However, not all edges in the forest are valid. For example, the edge ACC in the third state is not valid since the last non-terminal C cannot be rewritten by any rule to generate the next input symbol D. That's why we need to prune the invalid edges from the forest. In this example, we will prune the tuple ACC from the third state and remove the first state, since the first state is the initial state and does not correspond to any rules. After pruning the invalid edges in the forest, since there is only one parse tree in the forest, we can directly convert the forest to a sequence of rules that generate the input string. For example, the HACD corresponds to the rule A to CD. When there are multiple parse trees, we can also extract a tree from the forest efficiently. The correctness of the parser is formally verified in Coq. In practice, a rule may have many symbols on the right-hand side, but the 3 forms of VPGs are short and rigid. This is not very convenient. We provide a mechanism to make the forms more flexible, which are called tagged CFGs. A tagged CFG is basically a CFG decorated with regular expression operators and with tagged terminals. The users specify which terminals in the grammar are call and return symbols, and our tools can check whether the tagged CFG can be converted to a VPG. The following is the workflow. A tagged CFG is first checked by the validator. If the validator accepts the CFG, a translator then translates the CFG to a VPG with semantic actions. The VPG parser can then parse an input string based on the VPG and returns a parse forest. Finally, the semantic actions convert the VPG parse tree back to the original CFG parse tree. A natural question is how applicable VPGs are. To answer it, we analyzed all 239 grammars from ANTLR's Grammar v4 repository. We find that about 60% of them could be converted to VPGs. In the analysis, we manually mark the call and return symbols for those grammars. The analysis is conservative since we consider left recursion cannot be converted. Left recursion is common in practice. For example, an arithmetic expression can be specified as an expression plus another expression, which introduces left recursion. The left recursion can be resolved by other tools, and then it may be possible to convert the grammar to a VPG. We evaluate our VPG parsers and compare it with ANTLR and other handcrafted parsers. For evaluation, we took ANTLR's grammars for JSON, XML, and HTML and manually marked call and return symbols. Compared to ANTLR, our VPG parsers are 4 times faster in parsing JSON, 5 times faster in parsing XML, and 4 orders faster in parsing HTML. The HTML grammar does not exactly satisfy the official HTML specification, but is only provided by ANTLR as an example. We also compare our VPG parsers with other handcrafted parsers. Those handcrafted parsers do not have formal correctness guarantees. For parsing JSON, we evaluate 4 mainstream JavaScript engines, including SpiderMonkey, JavaScript Core, V8, and Chakra. Since we reuse the lexers of ANTLR, the total parsing time of our VPG parsers is approximated as the ANTLR lexing time plus the VPG parsing time. For parsing XML, we evaluate 4 popular XML parsers on NPM. In both charts, we can see that although the total time of VPG parsing is not the shortest, the parsing time itself is. The total time can be reduced by optimizing the lexers, and we left the further optimization for future work. In short, our VPG parsers are significantly faster than ANTLR's parsers and achieve performance that is competitive with other handcrafted parsers. As conclusions, we provide a derivative-based algorithm for converting a VPG to a deterministic PDA and a formally verified VPG parser generator in Cog. We also provide a conservative and sound algorithm for converting tagged CFGs to VPGs. Finally, our VPG-based linear time parsing is competitive with other handcrafted parsers.